Hello lovelies, in this video the brilliant Charlotte is walking you through my predicted paper for AQA A-Level Chemistry paper 3. Now this is a little bit of a beast of a video and there are some really good questions in here. I know it's not many people apart from me that are going to get really excited about really good A-Level Chemistry questions, but there are some really good questions in this paper. So if you haven't had a go at this paper already, what I want you to do is to pause after the question comes up, have a go at the answer yourself on a bit of paper and then play it and we can work through the answers together.
Hi there and welcome to this Primrose Kitten paper, A-Level Chemistry AQA paper 3, and this is your predicted paper. So this paper here has a mixture of multiple choice as well as your normal long format questions. Let's give it a go and see how we get on. Okay, so here we have got section A, and this first question is all about hydrated salts. So we're told that a sample of hydrated potassium sulfate with a mass of 2.458 grams has been heated to remove all the water of crystallization, and the solid remaining has a mass of 1.515 grams. And we're asked to find a possible formula for the hydrated potassium salt. So in this case, what I would recommend us doing is writing out a little dissociation formula. So we had our hydrated salt and we heated it and we ended up getting K2SO4 and X waters. So next what I would do is I would kind of fill in a bit of information here about what we have. So we know some masses, don't we? We knew the mass of the hydrated salt. We know the mass of the solid remaining is 1.515 grams. Now, the important thing about that is that means we can now work out the mass of the water due to the conservation of mass. So the mass of the water will be 2.458 minus 1.515. And that then leaves us with 0.943 grams. And that there is going to be our mass of the water. And the reason why this is so important here is now we can treat this almost a bit like how we would have treated an empirical formula question. So we know the mass, we know the MRs of these things as well. They tell us that the molar mass of the remaining solid, saving us a bit of time. They're telling us that it is 174.26. And water, of course, we know the MR of that, or we can work it out, is 18. So we can work out the moles of each of these things. And we will do that simply by dividing the masses by the MRs. So if we do 1.515 grams divided by 174.26, we end up getting 8.69 times 10 to the minus 3 moles. And likewise with the waters, we get 0.052 moles. So with this now, we are going to get something that we can use to work out what X is. We know, a bit like an empirical formula, the ratio now of the moles. But what we want is the simplest ratio, the simplest whole number ratio. So the way to do that is if we divide each of these now by the smallest number, which is the salt element, we will then get what X is. So we're dividing both of those by 8.69 times 10 to the minus 3, and we get 1 and we get 6. Okay, so that must mean then that that 6, what it relates to, is the number of waters that we have, which is our X. So therefore, the formula for the potassium salt in its hydrated form is going to be K2SO4.6H2O. And that X, or that 6 in this case, refers to the number of waters of crystallization. Excellent. So this next question asks us to suggest how a student doing this experiment could check that all the water has been removed. So the best way to do this would be just to continue to heat it or to reheat it and just to check that the mass doesn't change. If the mass continues to change, then yeah, we haven't heated it enough and there is still more water to lose. But we want to reheat it and check that the mass is unchanged. So reheat and check mass unchanged. Perfect. Okay, so 1.3. The entropy change of hydration for K2SO4 is 225 joules per Kelvin per mole. So we'll make a little note of that there. Delta S equals 225 joules per Kelvin per mole. So suggest in terms of the states of the particles involved why this entropy change is positive. Okay, so this is for the hydration of K2SO4. So this would be going from K2SO4, and we're going to add on this time those waters, so say the 6 waters, to make the hydrated salt. So we need to think, why would that be a positive entropy change? And with these enthalpy questions, there's 2 things we want to think about. One of them is how many moles there are on each side of the arrow, but the other is what the state of these things are as well. So in this particular case, we end up getting a hydrated salt coming from this sample of salt K2SO4. Now this salt here initially, before we add any water, will be a solid. Water is just a liquid, and the hydrated salt will be aqueous. So going from something that has solids and liquids to just aqueous means that we're going to have an increase in disorder. And that's because aqueous particles are more disordered than solid particles. So our answer for that part 1 will be that aqueous particles are more disordered than solid particles. Because solids, they're essentially fixed, aren't they? They can vibrate around a point, but they're not free to move, whereas aqueous particles will be moving throughout that solution. So aqueous particles are more disordered than solids. Okay, so part 2 here. Explain why K2SO4 dissolves in water at 25 degrees despite the enthalpy change of solution being endothermic. And they tell us there what that value is. The enthalpy change is 24 kilojoules per mole. And here, so if it's happening, despite the fact we wouldn't expect it to, this is all to do about whether the reaction is feasible or not. And feasibility always wants us to use the equation delta G equals delta H minus T delta S. And a reaction is feasible when delta G is negative, all right? So if we were to put the relevant numbers into this, we can check, well, does delta G give us a negative value? And if it does, then we can say, aha, well, yes, at that enthalpy and at that entropy, we do have a feasible reaction, and that is how it can spontaneously dissolve. So with this particular topic and this equation, I find there's a few things that people get wrong. And the main one refers to the units, because the units of H, or delta H, are the units of delta H are measured in kilojoules per mole. So kilojoules per mole is one thing, but then if we look at the delta S, well, the units of that are actually joules per Kelvin per mole. So we're not worried about the fact there's a Kelvin in the entropy, but it's the fact that one of these is in kilojoules and the other one's in joules. So what we really want to do is to convert, if we go back up here and look at what our delta S was, we want to convert that into now kilojoules per Kelvin per mole. And the way that we can do that is by dividing by 1,000. So if we divide that by 1,000, we end up getting 0.225 kilojoules per Kelvin per mole. That is exactly what we need to be able to use this equation, because in any equation that we ever use, we need to make sure that our units are consistent. Okay, so here then, we're going to substitute in our value. So delta G equals delta H, we were told, is 24. The temperature is 25 degrees C. This is another place where people could get issues. This formula needs it in Kelvin. So to convert from degrees C to Kelvin, we need to add 273, and that in turn gives us a temperature in kelvins of 298 Kelvin. So our delta G will be 24 minus 298 times by delta S, using the units that are in terms of kilojoules, 0.225. So we tap that away into the calculator and we end up getting that delta G is minus 43.05 kilojoules per mole. And the fact that that is negative tells us that the reaction is feasible. So if you weren't aware of that fact, that reactions can be feasible when delta G is less than 0, if you didn't know the equation for delta G, and if, most importantly, if you weren't aware of those units and what we need to do to the units to be able to use this equation, I would certainly make a flashcard of them, because this is something that is really easy marks once you know these facts. Okay, so let's try the next page. Okay, so question 2. A student wants to investigate the kinetics of the reaction between hydrogen peroxide and iodide ions in the presence of sulfuric acid. So we were asked to write the balanced chemical equation for the reaction between hydrogen peroxide and iodide ions, and they want us to include state symbols. So here we're doing it between hydrogen peroxide, we're expected to know, and we can see in the question that we're going to get H2O2 for hydrogen peroxide, which is aqueous, and iodide ions. So now we have an I minus. We won't worry until balancing, until the next step. And because it's in the presence of sulfuric acid, it says here, we're going to add on an H plus, which will also be aqueous. And then we need to think what we make when we react hydrogen peroxide and iodide ions. And we will end up making iodine and water. So iodine is aqueous in this case, and water is a liquid. So then we just need to have a look at balancing these. So we're going to need 2 iodines here. We are going to need 2 waters, and therefore we will need 2 H pluses. And that will be the balanced chemical equation for the reaction between hydrogen peroxide and iodide ions. Now, in case you're wondering sort of where this comes from, obviously you can work it out, but ultimately this is something that is taught. This refers to the iodine clock reaction, and this will be a specific reaction that it is very helpful to learn. So by all means do add this to a flashcard for the iodine clock reaction, because if you can just memorise it, and if you do think of the question, it does just say write the balanced chemical equation, then you will really save yourself a lot of time and energy. But let's have a look at the next one then. So here we've got the concentration of hydrogen peroxide is measured at different time intervals while keeping the concentration of iodide and H plus ions constant. We get the following results. Plot the graph of the hydrogen peroxide concentration against time in 10 to the 3 seconds. So let's have a look at the next page. Do this. So I've got our little table over here. So the first thing really we want to do is make sure that we label our axes. So along the x-axis, I'm going to put the time in the 10 to the 3 seconds. And along the y-axis, I am going to put the hydrogen peroxide concentration, and I'll put down the units as being moles per decimetre cubed. Don't forget to include the units when you do it as well. Now, important things when we're determining scale with these is we want to make sure that the axes is obviously labelled with units, also that the graph is going to cover at least half of the paper in each direction. So we don't want to do a teeny tiny scale. We need to make sure that we use at least half of the grid. So in terms of working out the axes along the bottom, I can see I need to go up to 10, okay? So I would say I would probably, along this bottom here, I would probably use each bit here as 2, 4, 6, 8, 10. And I think that is a sensible scale. It uses more than half of the page, so we're good. Anything more than that, and I can imagine it's going to be an odd scale that we use. So then moving upwards, looking at the numbers of these concentrations, I can see that the biggest number is 0.2. So I would want to make sure that I have it going up to 0.2. I would suggest here we need to be very mindful of the fact that if you look at these little squares, they're not the normal sets of 5, they're actually little sets of 4, which makes this quite horrible, to be honest with you. So we need to bear that in mind when we're dividing this up so that we get this sort of inner useful scale. And in this case, of course, there are multiple correct answers. I'm going to suggest we choose 0.04 and then 0.08 and then 0.12, 0.16 and then finally right at the top there 0.20. And I just feel like that's going to divide up easier than going up in say 5s, which would be what I would normally do, just because of the way these are divided. So here the first one is at time t equals 0, 0.2. Now that's going to be really quite an easy one for us to start with. Boom, just done. So then the next one now we need to do at 2 seconds 0.14. So 2 seconds 0.14. So that's going to be exactly halfway between the 0.12 and the 0.16. So already I'm quite happy with the scale that we've chosen here. The next point is at 4 and it is 0.09. So 4, 0.09, that's going to be just here. 6 is 0.06, which is going to be right between the 0.04 and the 0.08. And then at 8 seconds, it's 0.04. And then at 10 seconds, it's 0.03. So all in all, I'm happy with the scale that we came up with there. I think that was the best possible grid that we could have chosen. So now I would just do a curve of best fit to go through that. We want one continuous line. Perfect. All right, so now let's have a look at the next question. So now they want us to deduce the order of the reaction with respect to hydrogen peroxide and to find the value of X. So to do this, we're going to need to use our graph. So here we are, we've got our graph now. And to do this, what we need to do is to work out the half-life, okay? So they will be looking at your working with this one. So this method to work out the order, which is a great method, is the half-life. So if we look at the concentration and then we halve that concentration and we read down how long does it take for that to happen. And here I make out it's about 3.5, I'd say. So then if we do another half-life, so we halve it again, so halving it again would bring us to this point here. Read down, and then we need to work out, well, what is that difference here? And I make it exactly the same. If we were to do, say, 7 subtract that 3.5, we again get 3.5. So the fact here that we have worked out 2 half-lives and the half-life is constant tells us that the order with respect to hydrogen peroxide is first order. So first order would be our answer. So now for the next part, we are given a table of data and we're asked now to determine the order with respect to I-. So what we would normally do here is find 2 reactions where the other thing is constant. So in this case, the hydrogen peroxide, because if we do that, if we pick the 2 where that is the same, then we know that there's not going to be any changes due to that. So the rate won't change at all because the hydrogen peroxide has changed, because we've ensured we're only comparing ones where they are the same. So if we have a look here and we see, well, what has happened to the concentration of iodine and what has happened to the initial rate, we can see that both of these have doubled. So therefore, because when the concentration of iodine doubles, the rate also doubles, we can say that it is first order with respect to iodine. First order with respect to I-. Perfect. So now they want us to write down the rate equation for the above reaction. And rate equations always take the form of rate equals K times by each of the things which have an effect, each of the reactants which are affecting it. So we know that the hydrogen peroxide has an effect, and we know that that is first order. And so we just do to the power of 1, which we just don't even need to write. And then we also know it's first order with respect to iodide ions. So we again would just write iodide to the power of 1 essentially. So that would be that. So now they want us to calculate the rate constant using the data from experiment 2, okay? So we're just looking at experiment 2 here. So to do this, we need to take the rate equation from the previous part and rearrange it to get K as the subject. So K would be rate over concentration of hydrogen peroxide times by the concentration of iodide. And they've been specific, they've told us to use the data from experiment 2, so we're just going to use those data. I would recommend you always double check the units and check they haven't hidden in there times 10 to the something, because that's a very common place where people make mistakes. But here, nope, it's all just normal. So we're going to say 2.36 times 10 to the minus 5 over 0.05 times 1. And we would tap that away into our calculator to get our outcome, which I make 4.72 times 10 to the minus 4. And even though they haven't stated it here, I would work out the units as well. If you're unsure how to work them out, then I recommend you could just go back to that rate equation. And instead of putting in the numbers for rate and for the concentrations, I would put in their units. And then we can do a little bit of algebra to cancel them out and to work out finally what that unit is. 4 per dm minus 3. So here we can see that there's moles on the top and the bottom, and there's also a dm minus 3 on the top and the bottom. So that leaves us with that S minus 1 over mole per dm cubed. Now, because the mole and the dm minus 3 are on the bottom, we need to use our algebra skills to know that when we bring them back up to the top, we need to reverse the sign of them, which means that the unit of this in the end will be mole minus 1, because we're reversing the sign of just mole to the 1. dm minus 3 is going to become dm cubed. And the s minus 1 on the top is just staying where it is, doing what it is. So that is just the same. Okay, so here we're told that the student concluded that the H plus ions act as catalyst. And we're asked to explain whether the student's conclusion is correct or not. And the thing that we need to remember about what a catalyst is in these types of questions is that catalysts are used up but then reformed. So it's the fact that they are then reformed that is really essential. In this particular question, they are just used up, they're not reformed. So the fact that, so here when it says explain whether the student's conclusion is correct or not, we will say that they are incorrect, and we will say because they are used up and not reformed, because that is the really essential part of the definition of what a catalyst is in chemistry like this. So here we're asked to suggest a possible 4-step mechanism for this reaction and to write down the rate determining step first. So for these questions, we need to use our rate equation, okay? That's a really, really essential part of these questions. So we know that the rate is equal to K concentration of hydrogen peroxide and then times by the concentration of the iodide ion. And if we go back to what the original equation was, back in the first part of the question, we said that the overall equation is hydrogen peroxide plus 2I minus and 2H plus makes I2 and 2H2O. Now that's important because that is essentially what we need to make towards the end of this, okay? So we need to make some iodine, we need to make a couple of waters, and we need to use up hydrogen peroxide, 2 iodide and 2 H pluses. Now there's a lot of steps here, and I know this is a topic that a lot of people don't like, but I like to think of them as a puzzle. Now the first step is the important step, because here they tell us that the first step is our rate determining step. We need to know that our rate determining step uses the reactants that are in that rate equation. So only those are going to be the reactants in our step 1, and this is a really critical step to getting us started. So our first step has to be hydrogen peroxide, just one of them because there's only one of them in the rate equation, plus iodide ions, just one of them again because it's first order. And then this is where we now need to think. We need to think, well, what could that make? Those are the only things in the rate equation. So that's all that we have as our reactants in our rate determining step. Now this is where I would say keep one eye on what we need to make overall in our rate equation, okay? So overall we know we need some iodine and some waters. So if there's any opportunity to make either of those in this, we will do it. Now, we don't have enough iodines to make I2, but we do have things that could make water. So I would say, okay, I'm going to try and make one of those waters. And then I think, well, what else is left there? So we've got a spare oxygen left and an I minus. So we could say, okay, so we've made an IO minus as our other product there. We don't have to be experts. We are literally being creative with this and thinking, well, what's feasible? So that IO minus, I would look at our overall reaction that we're aiming for, and I'd say, well, there's no IO minus there. So what I'm going to do now is I'm going to take that and use that as a reactant in my second step, because then we're essentially getting rid of it. I would then take a little look at what our other options are in our reactants here, and I would say, well, what could I react with that? And I'd say, and I want to remind you here that there are other options to this, so please don't think that this is my only set in stone way for you to do it. I would look at this and I'd say, okay, what about H+? How about we have a go at reacting an H+? We know we've already reacted hydrogen peroxide, which was in the first step. We know we've already reacted one of those I minuses. So we've only got 2 reactants ready to play with here, or should we say 3? We've got 2 H pluses and 1 I minus. So I would say here, well, let's use an H+. What could we make with that? And if I look at the products that I'm meant to be making over on my equation, I can't really see any of those are going to get made. So I could just try and put these two together here. And I could say they could react together to make HIO. So then again, I would see that product I've just made, I'd look at the products in our overall reaction, and I would say, okay, well that isn't there again. So I'm going to use that now as a reactant in my third step. And I would have a look at what reactants I have left from my overall equation. I've just used one of the H pluses, so I've only got now two things really left. And I would say, well, maybe let's have a go now at an I minus. Again, I just want to reiterate, there's no definitive necessarily right or wrong way. So long as it does work out in the end, we should be good. But let's have a go at using an I minus here. So if I used I minus, I could see, again, one eye always on what we want to make. I can see I could make an I2 there. So I'm going to make an I2, and that leaves me with an OH minus. So now, if I look at what I've made overall, I know I've made one of the waters that I wanted, and I've made an iodine that I wanted. So I can scribble those guys out. I've made the iodine, great. I've made one of the waters, great. All that I have left now, and I've used up my last I minus, great. Now if I have a look at my third step, and I look at what I made, I can see I made an OH minus, which isn't in my overall equation as one of the products. So again, like before, I want to use that up. So I'm going to use it as a reactant in my fourth step to get rid of it. And if I look at my overall equation, I can see I've got one reactant left. I've got an H plus left. And I can see here that that H plus and that OH minus are going to perfectly balance together, react together to make H2O, which is exactly what I had as my last bit left in my overall equation. So I can look at that now and I can confidently say that those are my 4 steps in my possible 4-step mechanism. So there are other ways, give that a go yourself and see if you can work it out. But the idea is, if you were to imagine that there was like an imaginary line through the middle of all these, and you were to cancel all the things that came up both on the left-hand side and the right-hand side, you should be left with just what your overall equation is. But that was really good. That's quite a tricky question, that. So let's have a look at what the next question holds. So this equation here is another question referring to kinetics. Okay, so here they've given us a compound X, and they firstly here want us to name it. Okay, so we need to look at that and we need to see, okay, I've got this ring, which we're going to call phenyl. And I have also got here this group, which is a ketone. And if we try and work out what kind of ketone is that, let's count how many carbons there are. I can see I've got a carbon here and a carbon here, so that's going to be ethanone. The thing to sort of consider there is that this is a branch, and so although, yeah, you could consider, oh, there's another carbon attached actually to that ring, it's not a part of the branch. If there wasn't that double bond O there, it would just be like an ethyl group, wouldn't it? So here that's why we are going with like the ethanone. So the name of this would be 1-phenyl ethan-1-one. Okay. And next we're told to give the overall order for the above reaction. So to do this, you would have to have a look at its rate equation, and you basically look at each of the powers attached to the concentrations, because those powers represent the order with respect to those individual things. So here, both of those don't have a visible power, which means that they are each first order, and there's 2 of them. So it would basically be first order plus first order gives us second order. And that would be how we work out that one. Here we're told the initial rate of the reaction at 300 Kelvin was found to be 1.25 times 10 to the minus 4 moles per decimeter cubed per second. So that's the initial rate. And we were told that the initial concentration of reactants are shown below. Okay, so we're asked to calculate the value for the rate constant K for the reaction and to give its units. Well, to do this, we need to go back and have a think about what the rate equation will be. So from the previous part of the question, we were given that the rate was equal to K times by the concentration of C6H5COCH3 and H plus. Okay, so that was the rate equation. So you can see here that we have been told several things. We have been told the concentration of compound X initially, which is actually this big compound here. So we know the concentration of compound X is 0.02. We know the concentration of H plus is 0.15, and the rate, we were told in the body of the question, was 1.25 times 10 to the minus 4. So if we now just rearrange this equation, we will be able to find what K is. So K is going to be the rate over the product of those concentrations, and by substituting in the numbers there, we will get our rate constant. So it's going to be 1.25 times 10 to the minus 4 all over 0.05 times 0.15. So if we tap that away into the calculator, we get an answer equal to 4.16 times 10 to the minus 2. So next though, we need to get the units. And the best way to work out units in these types of questions is just to go through the formula again, but instead of substituting in numbers, substitute in the units. So for rate, we're going to put in moles per decimetre cubed per second. And for each of those concentrations on the bottom, we will put in moles per decimetre cubed. So the moles will cancel, one of the dm minus 3s will cancel on the top and the bottom, and then that will leave us with, if we bear in mind that anything on the bottom of this fraction, we need to reverse the sign of the power. So it was mole on the bottom, which is mole to the 1, and that's going to become mole to the minus 1. It was dm minus 3 on the bottom, but now because it's on the bottom, it will become dm cubed for the unit. And we had this s to the minus 1 on the top, which is just going to stay like that. So our calculation gives us the answer of 4.16 times 10 to the minus 2, and the units are mole minus 1 dm cubed s minus 1. Okay, so for part 2, we're asked to describe how the initial rate of reaction will change when the concentration of Br2 is doubled, but the concentration of X and H plus are unchanged. And the important thing here is to go back to our rate equation. And you can see here that the rate equation is dependent on two of these reactants. It is dependent on what X is and what H plus is. It is not actually dependent at all on Br2. So that means that because only Br2 is changed and the others are unchanged, there's going to be absolutely no change to the initial rate of reaction. So we're going to say no change. Perfect. So really good, really nice question there. So for this question here, we've told that we've been given the following mechanism that's been proposed for the overall reaction. And we want to suggest which of the 4 steps could be the rate determining step by using the rate equation. So just to write down that rate equation again, just to help sort of prompt us, that was that the rate equals K times by that C6, H5, COCH3 and H plus. And just to remind us that the overall reaction there was C6H5 COCH3 plus Br2 makes C6H5 COCH2Br. Okay, so we want to think, well, what would be the rate determining step? And the important thing to look at here is that the rate equation involves this compound here, the C6H5COCH3, and it involves H+. It does not involve Br. So for that reason, we can eliminate 3 because there's no Br2 in it, and we can also eliminate 4 because the reactant that it's got there does indeed still involve a Br, doesn't it? So that one we can eliminate. And either 1 or 2 would be fine there because they either use the 2 reactants that are within the rate equation or something that could be formed from those 2 reactants. So here for this question, your explanation would be either 1 or 2, and obviously you just need to state one of them, and your explanation would be that the rate equation doesn't involve Br2. So it doesn't involve Br2. Perfect. So that's good. Perfect. So now let's have a look at the next part to this question. So here we're asked to outline the mechanisms for both steps 2 and 3 by using curly arrows. So what I've done here is I've kind of added in the diagrams so that it can save us a little bit of work here. All right, so let's dive into the mechanism for step 2. So for step 2, if we expand out this structure a bit, just to help us out a little in seeing what is going on. So I'll keep this ring the same, but the CH3 I'm going to expand out. So we've still got our carbocation there, and I'll write that at the top, and I've got the OH down below. Now I can see, if I look at what it's got to become, I can see it has to become this double bond, and the way that we can do that is by doing a curly arrow from the bond between the carbon and the hydrogen here, and then putting it back to the bond. So we want to make it go to the bond, okay? So by doing that there, we have now added an electron essentially to that carbon positive cation, and we have broken the bond between the carbon and the hydrogen. So by doing that, we've broken one of the hydrogens and we now have a double bond. So that would end up leaving us with exactly what we wanted, double bond between those two carbons now. We've lost a hydrogen, one of them is only attached to 2 carbons, one of them is only attached to 2 hydrogens now, and then everything else is the same, which is exactly what we wanted for this particular mechanism. Okay, so that's the first one. So then with step 3 now, if we have a look at what has to happen with it, you can see that there's a couple of things going on here. One of which is that we now have a Br attached. That's one of the main things. And also we've got like a double bond between the O and one of the carbons. So between this region here, we've got a double bond, whereas we didn't here. Okay, so there's going to be something going on to both of those regions to make this. So again, like before, I would suggest kind of extending it out to show some of the additional bonds. So I'm going to extend this out, and then the ring will just stay the ring. Perfect. Okay. So now we can see, if we play a game of spot the difference, which I always think is valuable in these cases, I can see that in this region here, that oxygen needs to now form a double bond with the carbon. So what could happen there is the oxygen, which has a little lone pair attached to it, could then donate those electrons to the bond. And by doing that, from electrons moving from that oxygen to the bond, that is what consequently gives us that O plus ion and the double bond, because it's donated its electrons instead to that bond, so they don't belong to the oxygen anymore, making it a little bit positive. But we haven't broken the bond with the hydrogen, so that is still there. So then at the same time, I can see that the C-double-C bond essentially breaks here, doesn't it? And we know that we are reacting it with bromine as well. So I will also draw on a little bromine as well that is involved in this. And what we need to do really here is to break the bond, the double bond, and form a bond with the bromine instead. So the bromine is going to approach that double bond, become polarized, and then we're going to have a curly arrow going from the bromine-bromine bond to the delta negative, and you're going to have a curly arrow going from the double bond to the delta positive. Because by doing that now, we have now broke that double bond. That double bond is now just a single bond, and we have bonded it instead to the bromine as well. So that carbon is now a single bond, and it has a bromine attached to it, as well as just those other hydrogens, okay? So we have a bromine there. If we're doing skeletal formula, then we don't have to show those extra hydrogens, but of course you could write it in a different format as well. But that would be it, okay? So it's really important to have a look at what we have a look at what we need to get, and then to work out how can I do that. So in this case, there was just one curly arrow for the second step because we just needed to break one of the bonds between the carbon and the hydrogen to make a double bond. Whereas in reaction 3, we had to do 2 things. We had to form that double bond between the oxygen and the carbon, and we also needed to break the double bond and bond it to the bromine. And so as a result, as well as our final compound there in step 3, we also get left with a bromine ion as well. But that's really good, okay? Keep practicing those mechanisms because they're easy marks. You know, they really are something you want to be getting the marks for in your exam. Right, so question 4 now. All right, so polymers consist of monomers joined either by additional condensation reactions. And in 4.1, we want to name an example of a synthetic addition polymer and a synthetic condensation polymer. So this one here is really cool. So if you don't know this, then it's a perfect example where we can just stick it on a flashcard, okay? So I will write down one, but I will give you some other examples as well. So for an example of a addition polymer, then you could have, say, PVC. But there's many other ones you could say. You could say polyethylene, you could say polypropylene, you could say polystyrene, PTFE, PVA, Teflon, which is found on your pans. Now, all of those would be examples of addition polymers. So I would recommend you just write down a couple and just learn them so you have an example. Okay, so now for the condensation polymers, again, we're just looking for synthetic ones. So there's some examples we could know. One example we could say is nylon. So I will write that down. Nylon's often used in clothes. Other examples could be just polyamide, polyester, terylene, PET, PLA, Kevlar or Nomex. All of those would be perfectly suitable examples. I would just recommend you learn a couple that really jump out at you as good examples, the most memorable ones for you. Stick them on a flashcard and get memorising them. So for the next part, we need to do a definition here, okay? We're given a little flow chart and showed some reactions of an alpha hydroxy acid. But really here, we just want to be able to define the term stereoisomerism. So this is another one perfect for a flashcard if you don't already have it. And stereoisomerism are molecules with the same structural formula, but with different arrangements in space. So our definition is going to be molecules with the same structural formula. So really important, back that. Same structural formula, but with a different arrangement in space. So a different arrangement. We could be more specific and say of atoms or groups in space. And when we talk about stereoisomerism, generally that's either going to be referring to cis-trans or maybe optical isomerism. Those would be the two options where we see this situation where we've got the same structural formula but a different arrangement of atoms in space. So that is our definition for stereoisomerism. Okay, on to the next one. So this question here asks us to suggest the compounds of A and B, which are two stereoisomers. So what we need to know here is what will happen when we heat with phosphoric acid this particular compound. And what we're expected to know from this is that of all of the groups within this molecule, and we have an alcohol group here and a carboxylic acid, the group which will react with this heat and this phosphoric acid is going to be the alcohol. And what will happen is that is going to dehydrate this alcohol and turn it into an alkene. Okay, so that is the really important thing to note here. So originally it would have been CH3, CH2, CHOH, C double bond OH. But what's going to happen here is we are going to make an alkene from this. And of the positions where we could form it, because of the fact that that carbon with the carboxylic acid already it has a carboxylic acid group attached to it, it's not going to go to the right hand side, it's going to go here, okay? So what's going to happen is that little join there is going to turn into an alkene. So you will end up making a double bond here, and then that will just continue to be attached to our carboxylic acid. Now, whenever we have anything about cis-trans isomers, I would always recommend, and I've mentioned this in an earlier question, I would always recommend that we try and make it look a bit like the structure of ethene, because it's just easier for us, okay? So if in that case we have got this C-double-C bond, then we can have a look at what's attached to it. We've got an H here and we've got this carboxylic acid group. So I could write here an H and then a carboxylic acid group here. And then over on the other side, I could have a look at what there is. And I can see that, again, I've got an H and then I've got a CH3. Okay, so I've got an H and a CH3. Now what I've drawn here now is actually one of the isomers. And stereoisomers, because they've got the same structural formula, so it's got this same structure, but a different arrangement in space. In this case, because we have a double bond, that generally means it's going to be cis-trans isomers. So if we remember, that double bond restricts rotation, which means that if we did have it be made with a different orientation, it is actually a different molecule. So here, in this case, we'd have EZ isomerism. We can see that these are the two different isomers. So this would be, say, compound A, and this would be, say, compound B. Perfect. You could draw that in a slightly different format, but the principle is the same. It's to do with that relative orientation of these H's. So in one example, the H's will be on the same side, and in the other example, they would be on opposite sides. So then we're asked to give the full systematic name for compound A. And I would say here, of course, that's going to be relative, isn't it? You know, so they would be checking what it is for your example of A. And either that's going to be E-butanoic acid or it will be Z-butanoic acid. So for this particular case here, for my A, that would be Z-but-2-enoic acid, whereas for my B, that would give me E-but-2-enoic acid. So that would just be relative as to which position you put yours in. So don't worry too much which order it is, just make sure it's consistent and correct for your example. Okay, so this next one, they say that the alpha hydroxy acid, which we know has an alcohol group and a carboxylic acid group, can undergo polymerization with the monomer HOCH2COOH, which again has an alcohol and a carboxylic acid group attached to it, all right? So those are the important factors in this question, because those are what can react with each other, essentially here. So here we want the displayed formula of the repeat unit of a possible polymer using both monomers. Now, for this case here, I would say I would potentially sort of sketch them out initially and see what they would look like. So we already know really what the alpha hydroxy acid looks like, because we wrote that in an earlier part. And I'm going to just try and scribble that over here to make a bit of space. I'm going to just make a bit more space for us to play with here. So what I want to do is draw out that alpha hydroxy acid, and I will, in this case, unlike when I drew it earlier, I'm actually going to draw it so that the OH is sticking out the other side. So for the pure reason that by doing that, I'm going to be able to see a lot clearer how this bond is going to form, okay? Because it's going to be easier to sort of attach a carboxylic acid to an alcohol group of another thing if we can then sort of have them opposite each other. Okay, so that is the alpha hydroxy acid, and it can undergo polymerization with this other monomer here. So this monomer, again, I'm going to draw it. So this one here, I'm going to draw it with the alcohol facing the carboxylic acid and the carboxylic acid off the other side. And the reason why I have done this, obviously you might just really know how to do these inside out, not have a hesitation, just dive straight in and do it in full to begin with. But, you know, I would be safe here myself. I would circle off a water, because that is going to be the water that gets lost in this reaction. And then I would also, looking at the other two sides, do the same. I would say, let us get rid of an H from there and get rid of this OH, and they're going to be gone. Because you might be thinking, well, why am I doing that? But don't forget, this is forming a polymer, and a polymer is not just those two things. This is going to be repeating, repeating, and repeating, and repeating, which is why we want this repeat unit. So here, what we would want to do is now just draw that out, but without, obviously, the bits that I've circled. But that's good, let's try the next one. Okay, so here we're told that the following alkene reacts with HBr as shown below. And we have product X being what we make there. And we're asked, what is the name of the mechanism? And mechanisms always refer to, like, is it electrophilic, nucleophilic, addition, substitution? Maybe free radical substitution would be the only other sort of version of a mechanism that you could give as an answer. And so here we're expected to know that whenever we have that double bond, that CC double bond, the alkene, and we break it essentially, then we need to know that that is an electrophilic addition reaction. So our answer to this one here is electrophilic addition. And then we're asked to draw the structure of the product X. So when we break this bond, what is going to happen is we can attach both the H and the Br to that molecule in the same place where the double bond was. So here we will end up getting the ring, and attached to that would be a CH3 and a Br. Tidy that up a bit. And you may well choose that you'd rather write that in a slightly different way. You might prefer to have a proper look at it in terms of that double bond, and you might prefer to extend it out so you can actually sort of see everything that's happening there. That is something that may well you would choose to do. Whether or not you do, you will then still get the same outcome. Essentially what's happening is attached to that ring, you are going to break the double bond, end up with a single bond. You have an H still there, but then also a Br now, and then you've added an additional H to it. And that is where, in this case, the CH3 has come from that we've written, and also the Br that we've written. And of course the other H we don't have to write due to the skeletal formula. But that's good, perfect. Let's try the next question then. Okay, so here we have another reaction of an alkene with HBr. It's a different alkene in this case. And we're told that there's going to be a major and a minor product. And we're told to draw the displayed formula of the major and the minor products. So I guess the first thing to do really is to quickly check in and work out what is actually those products going to be in the first place, even just one of the products, and then we can sort of work out the other one. So at the minute you had that double bond there, and when the HBr reacts with it, an electrophilic addition mechanism is going to take place, and we're going to bond to that an H and a Br. And the Br could either go at either carbon basically, all right? And the major and the minor product is going to depend on which of those carbons it goes to. So here, if that bond breaks and attaching to this sort of second carbon is the bromine, then that in that case is going to be our major product, because whenever the bromine is nearer to the other methyl groups, and in this case the other methyl groups being here, the closer it is to those methyl groups, the more of them that it's made. So the major product is always the one closer to other methyl groups. So the major product is always the product where the bromine attaches to the carbon closer to the other methyl groups within it. So here we can see that would be one option. You could have written like little CH3s at each of these positions if you wanted to, but not essential due to skeletal formula. So that would be one version. I would call that our major product. And then our minor product would just be the bromine attaching to the other position within that molecule. So the bromine could instead attach to this carbon here, adding on that bromine, and then an H would attach at this other position, this other carbon. And so at the other positions, you'd still have the CH3s because they are absolutely unaffected. But just notice that it is all just about those two carbons either side of that double bond. We've still got those carbons here and here and here and here. And we're just looking at, well, which of those am I attaching the bromine to? Am I attaching it to the one at the end, like we have here with the minor product? Or are we attaching it to the one slightly closer to these other CH3 groups, which would be the major product? But those would be our solutions for part one there. So explain fully why product P is the major product of this reaction, while product P is the minor product. So this is a really good chance just to go over again and clarify why it is that the major product is the position where the bromine is closer to the other methyl groups. So what we want to know here is that secondary carbocations. So secondary carbocations, so those with the least number of hydrogen atoms bonded to them, are more stable. So that statement is really important that we know. So that is worthwhile sticking on a flashcard, I would say, as an explanation as to why certain major products form over others. So the secondary carbocation, so that with the least number of hydrogen atoms bonded to it, is most stable. And so we want to give a little explanation as to why that's the case. So that is due to a positive inductive effect of the methyl groups. So basically an electron is going to release from those methyl groups. So we're going to say it's due to the positive inductive effect of the methyl groups. And what that leads to then is that we reduce the charge density of the carbocation. Now, I would recommend strongly that that little explanation, which is almost like a little model answer, you turn into a flashcard, just as a generic explanation as to why any major product forms over a minor product. That is an absolute perfect answer. So brilliant. Let's have a look at the next question. Okay, so here we've been given a titration curve, and there's so much information within one of these. And we're asked which of the following mixtures could produce the above titration curve. So to work this out, what I'd recommend you doing is just looking at the general pHs of the beginning and the end, because that will give us an idea of what we're adding to what. Because at the beginning, that's what we have to start with, and at the end, that's as a result of what we've added. So we start at a very high pH. So I would suggest that we have a strong alkali there. And we end at a very, very low pH. So I would suggest that we're adding to it a strong acid. So strong acids would be things like hydrochloric acid, nitric acid, sulfuric acid, and strong alkalis would generally be the hydroxides. It would not be things like ammonia, because that is a weak acid with a pH closer to 7 than up in the air, like a really high pH. So in this case, our answer is going to be that maybe we're adding nitric acid to potassium hydroxide. So here we want to give the colour at the end point of the titration that is going to produce this curve. So we need to think, well, what would that colour change be when phenolphthalein is used as the indicator? And in this case, due to that change in pH, we're going to see it go from pink to colourless. Whereas when methyl orange is used as an indicator, it would go from yellow to an orange-red. And the key thing when looking at that titration on the other page is that it is going from an alkaline pH down to an acidic pH. And these are the colour changes for those indicators associated with that in particular. So we do need to know those colour changes. So if for any reason you're not sure of those, then this is something that is perfect to put on a flashcard. So that would be perfect to put on a flashcard. So give that a go. And then let's have a look at the next question. So the value of pKa for the aminoethanoic acid glycine is 9.87. Here we're asked to state the relationship between pKa and the strength of an acid. And here we really just need to know that the smaller the pKa, the stronger the acid. And if you weren't aware of that fact, then again, by all means, stick it on a flashcard. It's really, really useful information. So in part 2, we're asked to write an equation for the dissociation of aminoethanoic acid giving H+ ions. So here for this question, we're asked to write an equation for the dissociation of aminoethanoic acid giving H+ ions. And what we need to bear in mind here is that there's both, within this molecule, there is a basic part, the NH2, and a carboxylic acid part, which is acidic. So that means that when we sort of write down it in this dissociation, we need to bear in mind that the basic bit is going to act as a base and it's going to accept a proton. And likewise, the carboxylic acid part is going to donate a proton. So when we dissociate this, we know we want it to dissociate to give H+ ions. So when it does dissociate to give H+ ions, what we have is a donation, this time from the NH3 element. So that goes down to NH2, CH2, COO minus plus H plus. And that would be your answer to this dissociation. So now we're asked to calculate the pH of a 0.1 mole per decimeter cubed solution of aminoethanoic acid. So here we will first need to work out what Ka is to be able to calculate the pH. So we know pKa, and we know that Ka is then going to be 10 to the power of minus pKa. So in this question, we have got 10 to the power of minus 9.87. And we can tap that away into the calculator, and I make that 1.35 times 10 to the minus 10. So then we need to think, okay, how are we going to be able to work out then this question? How are we going to be able to get what H plus is? And because this is just a solution with this, this weak acid in it, what we can do is using our normal Ka equation, which normally would be H plus A minus over HA or something to that effect. In this case, we can use the approximation whereby H plus is approximately the same as that A minus. And therefore we could write it as Ka equals H plus squared over HA. But of course, don't forget that the HA in this case is referring to this acid, okay? So if we're being really proper, which we should be, and we rearrange this to get H plus as the subject, that's going to be the square root of Ka times by the concentration of that acid. So I've got to try and squeeze it all in here now. But you know, we should always really be thorough. Otherwise, the examiner will not like us and we will not get the marks. So the concentration of that acid, we're already told, is 0.1, and we've just worked out what Ka is. So here H plus will equal the square root of 1.35 times 10 to the minus 10 times by 0.1. So we'll tap that away into the calculator again, just like we've tapped in the rest. And we end up getting H plus being 3.67 times 10 to the minus 6. And then finally, to get the pH, we need to do minus log of that H plus, which will be minus log of 3.67 times 10 to the minus 6. And if we tap that in, I end up getting an answer equal to 5.43. So that there will be our solution. Perfect. Okay, so here they tell us that if we have 10 centimeters cubed of a sample and titrated it with 0.1 mole per decimeter cubed of NaOH, the pH of the solution was found to be 12.5 after an excess amount of the NaOH has been added. And they ask us here to sketch the titration curve for this curve onto the graph, okay? And this is all talking about what we just calculated in the previous part of the question. So we know from that last one that the sample from part 3 that we just did, it started at a pH of 5.4, and that's what we calculated as our answer in the previous part. And we know from what they have said here that it ends with a pH of 12.5. So the end pH is 12.5. And they also tell us that this happens when we add a volume of 10 centimetres cubed to it. And we know that it was down to 12.5 when 20 centimetres cubed had been added. So that means that when we want to put this all together now, we're going to start with a pH of 5.43, so somewhere around about here, and it's going to be vertical there and continuous. And then the vertical portion, which is called the end point, will happen when we add 10 centimetres cubed, so we're going to see a big jump now, and we know that it's going to finish at a pH of 12.5. So we know that we're going to see a big jump up here, and it's going to go up to 12.5, and then it will then stay constant. So here our final answer, and I will show you that again. So it is going to go along at about, so it's going to go along at about 5.3ish. 10 it's going to jump up, and then it's going to end at 12.5ish and end there at 20. So we'll just sort of finish it off at 20 there. Perfect. So see there, that is what we're looking for in this case. We just want to look at those few things. We want to look at what the pH is to begin with, what the pH is to end with, and where the end point is. But that was really good work. So now we get on to the next part of the paper, which is all about multiple choices. Section B is all about multiple choice questions. And with these, because they're just 1 mark, quite often you don't have to do the full calculation. You can use a process of elimination or deduction to solve. So keep an eye on that, okay? Let's have a look at question 6 here. So what is the oxidation number of iodine in HiO4? So here we need to use the fact that we know that H is +1, each oxygen is -2, and we have 4 of those. And HiO4 is a neutral compound and molecule. So in order to get the oxidation number of iodine, we need to think what is going to make the total of all these charges add up to make 0. So at the minute, on what we've got, that +1 and that -8, we have got -7. So that must mean that to balance and to make this overall go to 0, I must be 7. So the answer to question 6 is A. So for 7, which of the following is the electron arrangement of the strongest reducing agent? So here we need to remember that a reducing agent is something which reduces other things, okay? So that means it's the most easily oxidized. So the strongest reducing agent means we're looking at the most easily oxidized itself. And if we remember oil rig, that is going to mean that it's the most easily lost outer shell electron. So easiest to lose an electron due to our oil rig. So we need to look at these and think what is going to be the hardest to lose an electron. And if we think of, say, ionization energies and things like that, the factors are things like how much shielding is there, so how many shells are there, what is the distance from the nucleus, and what is the nuclear charge. Now if we look at these 4 here, we can see that some of them only go up to the 2nd shell, like this one here. Some of them only go up to the 3rd shell, like these 2 here, which leaves D, which goes all the way up to the 4th shell. And therefore the 4th shell is going to be the one with the most shielding, the biggest distance from the nucleus, and therefore the weakest attraction between the nucleus and the outer shell electron, and therefore it's easiest to lose the electron, making it the strongest reducing agent. So that would be our answer to 7. Okay, so 8 is a section of a polymer shown below. Which monomer could form this polymer? So we need to look at the options here and ask ourselves, how are we going to stick this together essentially? So here, if we look at these and we remember that, of course, this little stick here represents a CH3. If we were to have 2 A's next to each other, we have the potential here for a condensation reaction, which could occur between this OH and this OH here. Now, you might be thinking, but the orientation here, it has a CH3 at the bottom, but remember that we don't have a double bond between them, and it's double bonds that restrict rotation. We can change the order of that CH3 and that OH all that we like. So for that reason, A is going to be the answer, because that OH can come together with another OH, undergo a condensation reaction, which will be leaving you just behind with this O here. So let me just show you how that could look. And I am going to write it now in the orientation that the question suggests. I'm going to rotate that CH3 and the OH now. But if we were to put them next to each other, so you were to put that next to one with an OH down here now, then what we should see is this bond forming there, and then we have those repeat units. Again, that OH there would go, that H there would go, and we should see basically our repeat unit. You can see we've got here the stick going out, the CH3 there, a COO going to an O, and then again it will repeat onto the next one as well. So this is all an exact clone, albeit with a with the CH3 now at the top, but it's the same substance, okay? So all in all there, that tells us that A would be the monomer that would form that polymer. Okay, so here we want to say which element has induced dipole-dipole interactions, so London forces, in its solid lattice. And here, this is going to be the molecular structure compound. So here, if we look at magnesium, that is just magnesium, it's just metal, so it's not going to be that. That will have metallic bonds. Silicon, although it is a non-metal, it has a giant covalent structure, which means that the bonds between silicon atoms are going to be covalent, not dipole-dipole interactions. Whereas with sulfur, sulfur is also a non-metal, but it is a molecular structure. So sulfur, we will find, is the one that has induced dipole-dipole interactions. Okay, let's try 10. So a sample of NaOH is contaminated with an inert impurity. 4 grams of the NaOH sample was dissolved in 1 decimeter cubed of water, and a 50 centimeter cubed sample of the resulting solution was allowed to react with 50 centimeters cubed of HCl solution. The pH of the reaction mix was found to be 2. What is the percentage purity of the NaOH sample? So this next question here, I personally think is really quite challenging. And with these maths questions, I always think that the best thing to do in these sort of tricky maths ones is just to basically dive right into doing the maths. So let's do just that. So we know that the pH of the mixture was found to be 2. So we can work out straight away what the H plus concentration here will be, because that's 10 to the minus pH, which will be 10 to the minus 2, which is 0.01. Okay, so that's great. And then that is the H plus concentration once everything has been mixed. So we could work out how many moles that would be. So we know that to get that final concentration, we've mixed together the 50 centimetres cubed and the 50 centimetres cubed. So when we work out the moles, it's going to be that concentration times by the volume, which adds up to 100, divided by 1000. So that ends up giving us 0.001, and that is the moles of H plus once these things have reacted. So if we sort of make a little note of what the reaction is that's happening, you've got the NaOH reacting with the HCl. Doesn't really matter what it makes, but it's nice to sort of lay it out so we can check what the molar ratio is. So the moles of H plus, once these things have reacted, is 0.01. So if we do like our little ice thing, so after the reaction takes place, we have 0.01 moles of HCl. So what we can do now is work out, well, how many moles did we have of HCl before that reaction took place? So the moles of H plus at the start, we can go back to what we said. So we said that that was 50 for the volume times 0.1 for the concentration, and then divide by 1000 just to get the units consistent. So that leaves us with 0.005 moles of the HCl. So with this, we can look at this and say, well, if those things have reacted to give a pH of 2, then that must mean that you've only got the acid left at the end and all of the alkali has been neutralised. So we can say that after they've reacted, you've only got 0 left. And so if you think, well, what happened? What was the change when HCl went down from 0.005 to 0.001? And it went down to 0.00, and it went down by 0.004. So because it's a 1 ratio, the NaOH is going to go down by the exact same amount, which means that we can work out then what it was to begin with. So that means to begin with, it was 0.004. But the thing is that was just in our 50 centimetre cubed sample. So in 50 centimetres cubed, we have 0.004 moles of NaOH. But this question wants us to look at that original 1 decimetre cubed of water. And so we need to say, well, how many times does 50 centimetres cubed actually go into 1 decimetre cubed? And 1 decimetre cubed is 1000 centimetres cubed. So if we divide that by 50 centimetres cubed, we will get 20. So the moles of NaOH in 1000 centimetres cubed, or 1 decimetre cubed, is 0.004 times 20, which leaves us with 0.08 moles of that NaOH. Okay, so we're nearly there now. So that is how much we would need to react to form this pH at the end of 2. So now if we look at this, we can see that it was a 4 gram of an impure NaOH sample. So we could work out how many moles of NaOH were in that. We could say that the moles is the mass over the MR. So the mass is 4 grams. And the MR, we know by doing sodium plus oxygen plus hydrogen, gives us 40. So we end up getting the moles of 0.1. So that means that out of that 0.1, we only actually have 0.08 moles of NaOH. So the purity will be 0.08, what actually there is of NaOH, divided by the impure mass, which is 0.1, and then times by 100. And I end up getting there 80%. I think we'll all agree that probably seems like far too much work for 1 mark in a multiple choice. So please don't get flustered by these. Give them your best. If they take too long, sometimes it's best just to leave them and come back to them later. Okay, so for question 11 now, this one is a much quicker one, so you can see how they do balance out. A dilute solution of aqueous iodine is mixed with cyclohexane and left to stand to form 2 layers. So this particular one here is testing us on our knowledge of the colours for iodine. So this one here is purely a recall based one, basically. So we need to know that the upper layer is purple. So resting on the top of our layer is purple. And because this is a multiple choice, we don't even really need to have a think about anything else in this. Just the fact that that upper layer there is purple. So done. Lovely. On to the next one. Okay, so this one here is all about partial pressures and the equilibrium partial pressure. So looking at this, we're given a reaction. We're told the initial partial pressure of the H2S and CH4 are 200 atmosphere and 100 atmosphere respectively. And that's initially. Okay, so that means that we have in total there 300 atmospheres of pressure in total. Because if we add those together, that will give us like what the total pressure is. 300 atmospheres. Okay, so the mixture was allowed to reach equilibrium, and it's found that the equilibrium partial pressure of CS2 is 2 atmospheres, and that of the remaining CH4 is 98 atmospheres. What is the equilibrium partial pressure of H2S? So what I would recommend that we do here is do our little ice table again, really, because then we can work out how it has changed. So initially we didn't have any of the products, so initially the pressures were just zeros there. And we knew that it was 200 for the H2S and 100 for the methane. So if we look at the change in the equilibrium amount, the equilibrium partial pressure of CS2 is 2 atmospheres, and that of the remaining CH4 is 98 atmospheres. And the rest we don't know. But from this we can work out the change, okay? So here we can see that it has gone down on the reactant side by 2, and likewise it's gone up by 2 on the product side. And that is for 1 mole of each of these, okay? So if there's any bigger amounts of moles, it's going to affect it in different amounts. Now here we only care about the H2S. So because there's 2 of those, if you look at the molar ratio, there's 2 of those, so it's going to go down by 2 times minus 2. So we're going to get 196 there as our equilibrium partial pressure of H2S. So our answer to that one should just be D. Okay, so 13 is another quicker one to balance the calculation we just did. What is the colour of the CuCl4 2- complex? So the copper chloride complex ion. And for this one, purely recall, we should recognise that it is yellow. And if you don't know that, then please do make up some flashcards with those key facts on it. So how many structural isomers of C6H14O are tertiary alcohols. So we're looking at structural isomers here. What we want to do is I would start by writing out 6 carbons in a row, and always just start with that initial setup, okay, where you've got the simplest example basically. So here, let's just double check. So we've got 1, 2, 3, 4, 5, 6 carbons. We've got, and of course, for the sake of these multiple choices where we're just trying to eliminate things, I have not written in the H's. Please, whenever you draw it for your actual working, do include the H's. Of course, in a case like this, it is fine to be speedy because they're not going to look at your working. It is just a yes or no answer. But here we have got 13 and then 14 and then an O. So that's your first permutation there. So the next isomer we could do, and we'll do these ones a little bit smaller, is you could imagine that we have now just got it in a row, but this time the OH is coming off of the second carbon. Or we could do the same and imagine it was coming off of the third carbon. Now, beyond that, you could then put it on the fourth carbon, but that is actually the same as the third carbon again. You could put it on the fifth carbon, that's the same as the second again. Now, out of these, we would want to think, are any of these currently tertiary alcohols? This guy here isn't, it is a primary alcohol. This guy here isn't, it's a secondary, and so is this one. So far, we don't have any. So next thing to do is to try adding some branches on. So we know that all of these don't work, all of the straight chain ones. So now let's try doing a bit of branching. So the first branch, let's take it down just to 5 carbons now, and then put a branch on the second carbon. And then now we can decide, well, where can we put the alcohol again? And there's lots of options to go with here. We could put it on this first carbon. We could then give it a go, doing it all again. We could put it on this one here. Okay, so there you can see for this first one, we've still got primary alcohol. This one though, we do indeed have a tertiary alcohol because the carbon attached to the OH group is attached to 1, 2, 3 other carbons. So there you go, so we've got one there. So then we need to think, how many other ones might we have? So I can see there that if I was to attach it to this carbon, it's only a secondary. We need it to be attached to a carbon that has those branches. So let's try again. We've got 1 so far if we add to our little tally. So now let us try moving that branch elsewhere. So we had it on the second carbon. Let us now try doing 5 in a row, but with that branch bang in the middle, and then we'll see what we can do. And we're sort of getting a bit savvy now as to where it needs to be placed. We know that we would have tertiary alcohol if it was placed here. So that is another example. If we put it anywhere else on this chain, we would still be getting like a secondary or maybe a primary alcohol. So we need to look at more branching options, okay? So if we were to move that OH in that particular permutation, then we would end up back, if we moved it to the fourth carbon, that's the same as the second carbon. So now let's have a go at shortening it now just to 4. And let's have a go at attaching 2 methyl groups now to it. So in this case, you could have an OH group attached to one of these 2 carbons that are attached to methyl groups. And that in turn then would give you another example. That would give you another example of a potential tertiary alcohol. But of course, if you were to move it on to the next one, that wouldn't make any difference. So we're now at 3, and that is all that we will have. Because any more branching, any more little options that we might have here, you will notice that, oh, it's actually the same as one that we already have. Okay, so 3 is the correct answer for this one. And with these, it's best just to be methodical and just to move forward with it, and then you should be fine with it. All right, so that was really good. Let us have a look at the next question. So the table below shows some bond enthalpy data. What is the value for the enthalpy of formation of water in the gaseous phase? So where people go wrong with enthalpy questions, I find, is they'll say enthalpy of formation and they'll think, oh, I need to use a Hess cycle. But no, always look at the data that they give you. And in this case, they've given us bond enthalpies. So that means that that is what we need to use. So I would first write out the balanced equation for the enthalpy of formation of water. And remember, formation of water, or formation of anything, is the energy required to form 1 mole of a substance from its elements in their standard states and conditions. So that's going to be half of the oxygen plus an H2 gives us H2O. So that means that we have an H2 molecule, so that's an H to an H. You've got half of an O to an O, and then if we had H2O, you can see that we have 2 OH bonds. So to do bond enthalpy calculations, we say that delta H is equal to the bonds broken minus the bonds made. So the bonds broken are going to be H to H, so 436, and a half of the 496. And then we subtract the bonds made, and in this case we've got 2 of the H2O bonds. Now I wouldn't rush this with the maths. I would calculate this nice and slowly because, again, very easy to make mistakes if we rush. So I get here 684 minus then 2 times 464, so that's 928. So if I do 684 minus that answer, I get minus 244, which there you can see is A. So that would be our answer to that first part. Okay, so 16, a phosphate buffer contains H2PO4-, which acts as a weak acid. What is the value of the concentration of HPO42- over H2PO4-, which is needed to maintain the value of a pH of 7.4? So here we use the fact that Ka equals, and then generically it would be H plus A minus over HA. So we need to think, what would the actual dissociation of this be? So we're told that the H2PO4- is the weak acid, and a weak acid dissociates, doesn't it? So then we end up getting H plus and HPO42-. So in this place it should be H plus HPO42- over H2PO4-. And we're being asked to find the ratio of the HPO42- over the H2PO4- concentrations. So to see that, we need to essentially get that on its own. We need to get rid of this H plus. So that means that what we want is going to be equal to K minus, and then we can just divide through by the H plus. We don't have to worry about this looking weird, because it does look a bit weird, but that's okay. So that's Ka over H plus. Now in this case we're talking about a pH of 7.4, and we know we can work out H plus concentrations using that pH. So that's 10 to the minus pH, which in this case is 10 to the minus 7.4. So in this case, that ratio is going to be equal to 6.31 times 10 to the minus 8 over 10 to the minus 7.4. So tapping that away into the calculator now, I get an answer equal to 1.58, which is helpfully B. Okay, so the answer to that one there is B. 17 is just a balancing question here, I think. So they've given us half of it balanced already, which makes our life so much easier. We can see that we know we have 3 coppers. So for that reason, we know that we have to have 3 coppers as well on the other side, don't we? So straight away, even without doing anything more, we know that the answer is B, because that's the only option that has X down as 3. We can look at the rest just for the sake of it, but I do want you to know that this is kind of what they want you to do in these multiple choices. Some of them will be like the previous one, 16, where we had to do some maths. There was no getting away with that. But some will be like this, and these are the ones that save you time. So just to show that it works the whole way round, we need to find the amount of NH3s. So if I just look at how many N's we have there even, I can see I've got N2, so therefore Y has to be 2, which just supports what we've just said. Okay, so that was really good. Not too tricky, that one. Okay, so here we need to think, what are the favourable conditions for spontaneous reactions? And this is a great one, really. They're really, really helpful. It all comes down to this equation that delta G equals delta H minus 2 delta S. And we need to know that for a reaction to be spontaneous, delta G has to be less than 0. It has to be negative. So given that, this is where we can rearrange this equation to get a little equation that we've got here. So see, all that I've done here is I have said, well, if delta G is less than 0, then this delta H minus T delta S is less than 0. And then I've rearranged it, okay? So I happen to have added to both sides the T delta S to get it on the other side. And then I end up getting delta H is less than T delta S. Could be written in a different permutation as T delta S is bigger than delta H. But the point is we have now eliminated two potential answers. It can't be B because that said equals, and it can't be D because that also said equals. So that leaves us with two options here, and we need to think, okay, it comes down to if delta S is going to be positive or negative. And we know that because the delta H's are the same either way. So we need to think of this, this little equality that we've got here, which we have just said, T delta S must be bigger than delta H. Well, if we know that T times delta S must be a bigger number than delta H, and we know that delta H must be positive because, hey, that's the only option that we've got here. We can clearly see both of these suggest that it has to be positive, so it must be. So delta H is positive. T, we know because it's measured in kelvins, is always positive as well. It's always bigger than 0. So delta S has to be positive to give it any chance of being correct. If it was negative, then T delta S would be a negative number, which certainly is not bigger than delta H. So for that reason, our answer to this question would be A. Okay, so for 19 here, 3 gaseous equilibria have equilibrium constants K1, K2 and K3 respectively. What is the relationship between K1, K2 and K3? So let's not forget here that equilibrium constants are essentially the concentration of the products over the concentration of reactants. So in this case, that would be like K1 equals, in this case, the products would be AB squared over the reactants, which is concentration of A times concentration of B. That would be what K1 is. And then K2 then would be concentration of C squared over the concentration of A times the concentration of B squared. And then K3 will be the concentration of C squared over the concentration of AB squared times by the concentration of B. Those are what those are, using our standard what the equilibrium constant are. And now we need to think, putting these together, which of these could be right, which of them could be wrong, okay? So K1 equals K2 times K3. If we imagine timesing those together, could they equal each other? And I would look at that and I would say no. If I do K2 times K3, then the C's on the top are going to multiply together and end up giving us C to the 4, which we don't want. So I'm going to eliminate A here. So next, K2 equals K1 times K3. So if I were to multiply together K1 and K3, that would end up looking like AB squared over A times B times by concentration of C squared over the concentration of AB squared times by B. Now putting those together, I can see that my AB squareds are going to cancel, and this will simplify to give us C squared over AB squared, which, as it happens, is exactly the same as K2. So that means that yes, indeed, B is correct. And we don't need to go through the rest. If we reach that point and we know that it's correct, then we have done our job and we can move on to the next question. Okay, let's see what we've got. Okay, so identify the major product for the following reaction. So this here is going to take this alkene and it's going to make an alcohol group. So straight away we can see, looking at all of our options, I can see that D doesn't have an alcohol group on it. So you know what, I'm going to eliminate that one straight away. And now I've got a 1 in 3 chance of getting this right already. So the next thing we need to think, okay, so major and minor product. The two options are going to be the position of that OH. Either the OH will attach to here, or the OH will attach to here. So we need to think, well, which of those two would be our major product? And even, are any of these going to be represented here on the page? I look at this and I don't think C still has in it this trimethyl group. So all these other ones, I can see a trimethyl, I can see a trimethyl. I don't see a trimethyl because here we've got like a stick before it then goes onto that CH3. That's an ethyl group. So again here, I'm going to eliminate C, not because of anything to do with the minor or the major, but just even simply thinking if I'm going to do this reaction, C doesn't represent what it should be. Which of these will form the major product? And with this, we always want to bond the group on, so in this case that OH, in a position closest to the most methyl groups basically, okay? So in this case, out of those two options, I would say that the one nearest to the most methyl groups is going to be that OH there. When it's not on the end, it's on the second carbon instead. So looking through these, I can see that this here looks like the most likely option for that. And so I would say A. I wouldn't say B because that OH is right on the end, which to me looks like it has stuck on right on the end there. So there we want to choose the major product to be the group where the OH or the bond, whatever the bond is that we're attaching, is attached to the carbon closest to the most methyl groups. So the answer to this one would be A. Right, so here this is a standard electrode potential question. And they're telling us that the standard reduction potential for the half equation, M3 plus 3E minus makes M, at 25 degrees is one of these options. So what we need to notice here is that they've given us almost like the overall reaction here as a part of the question. And we know that we can get the overall reaction basically by doing the most positive of the electrode potentials and subtracting the most negative. So here in this case, we're told that the standard reduction potential is what we're looking for. And we would expect the reduction potential to be the most negative of the two. So straight away there, we can eliminate C and D. Now we're just between A and B for this question. So an important thing to notice is that in the overall equation at the top here, we've got 3 Ag pluses making 3 Ags. And if you compare that to this reaction, we actually need 3 of them, okay? So that means that that electrode potential cell, rather than using 0.8, we're doing 3 of those, okay? So in this case, that overall potential, which is going to equal the 2.46, is going to equal the most positive, which is actually 3 times 0.8 minus that most negative one, which is the one that we're trying to find. So in this case, then we get 2.46 equals 2.40 minus our mystery number, let's call it x. So if we were to rearrange this equation now, or even just by observation and comparison, we can see that our answer should be A. Okay, so that would be our answer. It's a really handy trick just to know that we can calculate the overall electrode potential just by doing the most positive minus the most negative. It's a simple little trick. So next we have to analyse this next question and see, well, which of these compounds can be oxidized by acidified potassium dichromate solution. So we need to remember, what can we oxidise with potassium dichromate? And we know we can oxidise certain alcohols, say like primary and secondary alcohol, and also aldehydes, which we can oxidise to make a carboxylic acid. And we also are looking for things that can give a positive response to Tolling's reagent, and that is going to be aldehydes. That's the silver mirror test. So here we need to look through these 4 things and decide, well, which of these would give these 2 results. and we need to look at these options to see what corresponds, okay? So here we can see that the first one has a ketone and an alcohol. So the alcohol would get oxidised by acidified potassium dichromate, but nothing there is going to give a positive result to Tollien's reagent. So straight away we can eliminate 1, which means we can eliminate B and D. So then for part 2 here, we have got CH3, CH2, CHO. Now that is an aldehyde, and we know, don't we, that aldehydes can be oxidised, and they also give a positive result to Tollien's reagent. So we look at that, but oh, that hasn't even narrowed us down. So actually that wasn't even important. Now what we want to do is to look at either 3 or 4, just one of them would do, because then we can eliminate. So this next one, CH3, CHOH, CH3, well that there has an alcohol, but it doesn't have an aldehyde. So because it doesn't have an aldehyde, we know that 3 isn't going to give a positive result to Tollien's reagent. So we can eliminate C as well. So here our answer would be A. Right, so this next one's a bit unusual, and we don't often see questions like that, which is why it's so good that we get to have a look at it now. So we're told that we have a pH of a solution 1, and we're asked to find its H plus concentration in parts per million. So to work out parts per million, that is almost like a version of a concentration, but instead of it being in the normal moles per decimeter cubed or something, it is what is the proportion of it out of a million. Okay, so it's a bit like a percentage, but instead of it being a percentage, it's out of a million instead. So to be able to do this, we need to work out, well, what is the H plus concentration? And we can do that by saying H plus is 10 to the minus pH. And that leaves us with 0.1 moles per decimeter cubed, because the pH is 1. Okay, so here, because we're given a density, what we really want to do is to try and work out what the mass of this is within this. So we could say, okay, we have, due to this concentration, we have 0.1 moles in 1 decimeter cubed. Okay, so we can work out the mass by saying moles is the mass over mR, so mass is moles times mR. mR of H plus would just be 1. So we could say we've got 0.1 grams in that 1 decimeter cubed. Now, we can also go back and think of what they tell us the density of the whole thing is. So the density of the whole thing is 1 kilogram per decimeter cubed. Now that means that the solution in total, 1 kilogram of it fits in that 1 decimeter cubed. So we need to think, well, how much H plus is there in this whole solution? We've got 0.1 grams out of 1 kilogram, which is 1,000. That is our proportion within it. Now, if we times that by a million, then we will see how many parts of it per million there are. So we're now going to just times it through by a million, tap it away into the calculator, and we should get 100. And that would be our solution to this one. That is what the concentration for H plus is in parts per million. So a very unusual question, a really good one for us to have a go at there. Okay, so which substance is produced by a redox reaction when solid sodium iodide reacts with concentrated sulfuric acid? And this one here is just something really that we're expected to just know off by heart, to be honest. So we need to think sodium iodide plus H2SO4, and we need to ask ourselves, well, what does that make? So here it's likely that we will end up reacting, making some iodine, some sulfur dioxide, some sodium sulfate, and some water. And so in this case then, we can see that the answer would be A. It's going to be I2. So for 25, we're told that 15 grams of a group 2 metal reacts with an excess amount of aqueous HCl acid. So here we've got our classic metal plus acid, and we know that that makes a salt and hydrogen. So it tells us here that we had 15 grams of that metal, so I'm going to write that in. We know that the volume of hydrogen gas given off is equal to 61.2 meters cubed, and we know that the pressure is 25 pascals, and we know that the temperature is 300 Kelvin. They tell us what the gas constant is. So all indicators there tell us that we're going to have to use PV equals nRT to find the number of moles. So moles would be PV over RT. So we tap away in our calculators. We're going to do 25 times 61.2 over 8.31 times 300. And we'll tap that all away and we'll get that the moles in this case is equal to 0.614. Now, because this is a group 2 metal, if we were to look at the balanced equation, we would need 2 times the acids compared to the metals. But the molar ratio between the H2 and the metal would be the same. So the moles of the metal will be the same. So now we can get to work with working out what the MR is, because moles is mass over MR, so therefore the mass over the moles will give us the MR. We can say 15 over 0.614. We can tap that away in our calculator and then we will get an outcome. And I make that 24.4 grams. And so this is where we would now have a little scoot over to our periodic table. We would have a look at the mass numbers, and I can see that magnesium is 24.3, which is pretty much what we want it to be. Remember, there's rounding, there's measurement errors and everything. So here I would say that the solution to this one is magnesium. So then for 26, we are asked which one of the following could act as a ligand. And the important thing to know about ligands is that we need to have a lone pair of electrons on one of the atoms. So out of these, the only one that is going to have a lone pair of electrons available is going to be C, NH2 ion. So in 27, which amine has only 3 peaks in its proton NMR spectrum? So that means that we only have 3 proton environments. So in this particular one, you may find it easier to draw some of them out to make it a bit easier. You know, we've got methylamine. I think it's quite clear from that because it's only got one methyl group and then the amine. You can see there's only 2 proton environments. You've got those 2 H's in the amine and then you've got the 3 H's within the methyl. So that's only 2, so straight away we can eliminate that one. So next though, we need to have a look at the next one. So diethylamine. So we have got 2 ethyl groups coming off of our amine, each of which are going to have lots of hydrogens associated with them. So because it's a diethyl, we're going to have some groups here. The ethyl groups are both identical, but within each ethyl group, you've got different hydrogen environments. So these 2 would be the same, and then also these guys will also be the same, all these protons, but then the proton within the amine group is going to be different. So straight away, without going any further, I can say that my diethylamine is going to be the correct answer. So here we're told that complete combustion of 20 centimetre cubed of gaseous hydrocarbon X requires 180 centimetres cubed of oxygen, 120 centimetres cubed of carbon dioxide forms, and all gas volumes are at room temperature and pressure. Now this is all about molar ratios, all right? So we've got this gaseous hydrocarbon X, and we know it is undergoing complete combustion with oxygen, and we're making some carbon dioxide. Now, obviously it's going to make water as well, but that isn't a gas, so it's not going to contribute to the gas volumes. So here we are told that we have 20 centimetres cubed of the gaseous hydrocarbon, 180 centimetres cubed of oxygen, and 120 centimetres cubed of carbon dioxide. Now, we're talking about gas volumes here at room temperature and pressure. So of course we have got the standard equation which says that the volume equals the moles times 24 decimetre cubed. Now that's important, but really all we need to take from this is that the volumes are going to be directly proportional to the moles. So here we've got these volumes, we can cancel these down to get the simplest ratio. We can divide each of these through by 20 because they're all divisible by 20. So we're going to get 20, we're going to get 9, and we're going to get 6. Now, if you imagine that we had like little balancing numbers in front of all of these then, and these are the balancing numbers. We've got 1x, so we don't need to write anything in front of that. We have got 6 CO2s and we've got 9 O2s. Now from that, we can balance the whole thing now, because we know we've only got 1x. So 6 carbons, great. Well, already then, we know that this is going to be C6, because that's how many carbons we get from this 6 CO2. Now, if we look at the answers, that eliminates then A and B, but we do still have the options between C and D, so we can't just stop here. We've got to go an extra step. So if we add up how many oxygens we have in total here, so we're going to have 12 from here, we have 18 from here, so we know that we're going to need another 6 over here as well. We need 6 H2Os, which gives us 12 hydrogens, which means that our formula will be C6H12. So our answer here is C. So see, we didn't actually need to do any calculations, just understanding that under that room temperature and pressure, the volume is directly proportional to the moles. Right, so let's have a look at question 29 now. So we're told that hydrogen bromide reacts with 3-methyl-butanene, and we're told to find the structure of the major intermediate formed in the mechanism. So this question here is coming back again to the idea of majors or minors and understanding which is the most stable carbocation, okay? We need to know that as the order of primary carbocation to secondary to tertiary, it gets more stable. So let's just remind ourselves of that before we progress. So a tertiary carbocation would be one where you've got, say, 3 methyl groups attached to your carbocation. Secondary, you just have 2, and primary, you would just have the 1, okay? So that's going to be important in this question for determining what's going on, okay? So if we have a look at this, and I would start off just by writing out what 3-methyl-butanene is going to look like, all right? So that is going to look like this. It's going to have 2 groups here. I'll sort of unveil all this in a minute. So it's butene, so it has got 4 carbons in a row, hasn't it? These are those 4 carbons in a row. And it's got that methyl group, which is this one here. And then, of course, got all the hydrogen surrounding it as well. We don't want to forget about those. So if we have a look at this here, we need to decide, well, when we react with the hydrogen bromide, where will the hydrogen react with, which carbon of that CC double bond, and which carbocation will we form? So in this case here, if we look at this carbon, this first one, we can see if the carbocation formed there, we would just have a primary carbocation. Whereas if it formed over here on this one, we would have a secondary carbocation, which is more stable. So that means that the hydrogen from this HBr is going to attach to the CH2, the carbon which is to the left-hand side of this alkene bond, and that's going to form a CH3, which will then attach to carbon, which we're saying is going to be our carbocation, which has that little H attached to it, and then goes on in skeletal, half knot form that this seems to be in. And so the reason why it forms there on this carbon in particular is because that is a secondary carbocation, which the alternative would have been a primary carbocation, and a secondary carbocation is more stable than a primary one, so more likely to form. So for that reason here then, we have got, if we look at our thing, we have got D, okay? So likewise, we could have eliminated some things as well. You know, if we look at, say, C, you can see that the carbocation formed over here, which why on earth would it do that? That's nowhere near the alkene bond, so absolutely no reason under the sun why that would have been the case. We could have eliminated that right away. The same with B actually, you know, where the carbocation forms there, that would be equivalent to this little carbon hiding in here, which again isn't actually attached to the double bond, to the alkene bond, and therefore why on earth would that have been it? So we could have eliminated those straight away. The only possible options would have been A and D, which of course would have brought us back to which is the most stable of the carbocations, okay? So that was really good. I hope this is reinforcing your understanding of stabilities and these formations of minor and major intermediates. But that's really good. Keep at it. Let's have a look at the next question. Okay, so 30. 0.036 moles of aluminium was allowed to react completely with HCl to form an aqueous solution of aluminium chloride. The volume of hydrogen gas in decimeter cubed at room temperature and pressure is... So here we need to do like a little balanced equation. So we've got a metal reacting with an acid, and we know that that makes a salt and hydrogen. So then we just give this a little balancing here. We would need 6 of these, we would need 3 of these, we would need 2 of these, and we would need 2 of these. Checking that over, that all looks balanced, so I'm happy with that. But now we need to think, well, we know that we had to begin with 0.036 moles of the aluminium, and using the molar ratio there, we could work out how much hydrogen there's going to be. So here we can see that we have a 2:3 ratio between the aluminiums and the hydrogens. So if we know that we have got 2 aluminiums, so 2 parts of that ratio equals 0.036. So then we just want to work out what 3 parts of that ratio will be. So we would halve the 0.036 and then times that by 3, which leaves us with 0.054. So we know that the moles of hydrogen is 0.054, and using our relationship that states that the volume is equal to the moles times 24 decimeter cubed when we are at room temperature and pressure, we would just say that volume equals 0.054 times 24. So tapping that away into the calculator, we get 1.296. So our answer to this one is A. Okay, so here we want to say, what is the shape of SiO4 4-? And for this particular one, of course, maybe this will be one you're familiar with and you just know it. I always like to do like a little dot and cross diagram though. So normally silicon would be, it has 4 electrons in its outer shell, doesn't it? So 4 electrons in its outer shell, and oxygen normally has 6 in its outer shell, so it has to gain 2. So in this case though, obviously it's O4 4-. So imagine that each oxygen was like an O- ion instead. That means that each of those oxygen atoms has gained 1 electron. So rather than it having 6 electrons in its outer shell, it actually has 7, okay? So that means then that if we were to do the little oxygens around it, then that means that we would indeed get, because we use no minus ions in this case, although minuses, we do get those full outer shells. And so we end up getting 4 bonded pairs that surround silicon. And we are expected to memorise that when we have 4 bonded pairs of electrons, that means that we have tetrahedral. Okay, so tetrahedral would be our answer. Okay, so for 32, we're told that a buffer solution of pH 5 was prepared by mixing equal volumes of 0.1 of a monobasic weak acid and 0.1 moles per decimeter cubed of a sodium salt of this acid, so it's conjugate salt. And the pH of the resultant solution when 20 centimeters cubed of this buffer solution was mixed with 90 centimeter cubed of 0.1 moles per decimeter cubed of a weak acid solution is what pH? Now there's a lot of stuff going on there. I think that's quite a daunting question, to be honest with you, but it shouldn't be as hard as it looks. Remember, it's just a multiple choice question. Right, so here we need to think that these concentrations given to us at the beginning, they are of not the buffer solution, they are of the salt and acid. So what I would probably do here to start off with is just write down that dissociation of the buffer solution. So I've got HA dissociates to H plus A minus, just a generic formula here. And what we can do is write down initially in this 20 centimeter cubed solution of the buffer solution how many moles we have of the acid and how many moles we have of the salt. But one thing I've noticed with this question is because those concentrations are given of the actual of the weak acid solution, the salt solution, but the 20 centimeter cubed is of the buffer solution, we want to imagine, due to the fact there's equal volumes, that basically 10 centimeters cubed were coming from each of those 2 parts, which means that in our calculation when we do moles, it's concentration times volume over 1,000. We'll use those concentrations of 0.1, but for the volume we're just going to use 10. So here when we do that, we end up getting moles equal to 0.001 for both of them. So that's before we add this additional amount of weak acid solution. So now if we also work out, well, how many moles do we get of this weak acid solution? So that's going to be the concentration times by the volume, divided by 1,000 to adjust for those units. And there I end up getting that we're adding on to that 0.009 moles of the weak acid, which means that in the end we end up having 0.01 moles of that weak acid, but still the 0.001 moles of the A minus of the salt. So with this, we know that we have equal volumes of both the weak acid and the salt to begin with. And so initially, because we had the same concentration of them as well, the same number of moles of them, we could have said that Ka was H plus A minus over HA, but because those concentrations were the same at that point, they would essentially just cancel out. And we could have said that the Ka for this scenario is equal to H plus concentration. And we can work out the H plus concentration, can't we? Because H plus concentration is 10 to the minus pH. So we know the Ka for this particular acid is equal to 10 to the minus pH, or 10 to the minus 5 for this case. So that means that we can go back to our Ka equation with these new facts that we know, use it in the rearranged format to find the H plus concentration, and then we get Ka HA over A minus, and we can insert now the Ka that we know is 10 to the minus 5, and the concentrations for both the weak acid and the salt. Now, in this case, especially this being a multiple choice questions, because we have them in the same solution now, so the volume of them are essentially the same, it's in this same body of solution. We don't really need to work out the concentrations because the concentrations would actually cancel. The moles in this case, because they're in the same volume, are going to be proportional to the concentration. So we can just stick right in here what we know to be the moles, and due to cancelling, because we've got the same amount of concentrations on the top and the bottom, then we will see that it will work out just fine. So we're going to do 10 to the minus 5 times 0.01 over 0.001, and we end up getting an H plus concentration equal to 10 to the minus 4. And if we say pH equals minus 10 to the H plus, we end up getting here a pH equal to 4, which is our answer for this one here. It's quite a tricky one, to be honest. It's not one that I would spend too much time on if you felt flustered towards the end of the paper, but it is what it is, and that is how we would solve it. Okay, so this one is a topic that I really like. I really like how this one applies to a bit of maths and how y equals mx plus c. So here we've got the graph of ln k against 1 over t for a reaction has a gradient with the numerical value of minus 3250. And they want us to say, well, what is the activation energy for this reaction? So for this, we need to know the rewritten Arrhenius equation, the one which has ln k as the subject. So that equation goes that ln k is equal to minus activation energy over R times by 1 over T plus ln A. Now the important thing here is that if we're plotting a graph of ln K against 1 over T, then that is equivalent to, say, y over x, isn't it? So that means that we can compare this equation to y equals mx plus c. And so in this case, our ln K would be equivalent to our y, and our 1 over t would be what is equivalent to our x. So the gradient would in this case be the same as that minus EA over R. So that's the activation energy. So the gradient, which would be our m in our normal y equals mx plus c equation, is comparative to that minus activation energy over R. So minus activation energy over R. And to be honest, you can just learn that the activation energy is equal to the gradient times R. That can be a thing you just learn. So here we're going to say that if we take that gradient, and we'll just take the positive value of it because the negatives will cancel in this case, we've got 3,250 And now we just want to times it by R, which is 8.31. And so we will do that quickly. And I make that 27,010. And that is me rounding that to make it a bit more consistent with the results, but that is fine. So that activation energy is in joules per mole. Of course, here you might be thinking, oh, but it's a little bit different, but this is in kilojoules per mole. So all we need to do there is divide it by 1,000, and you will see there that we get this 27.01. So that would be that bit done. So now we have got question 34, and here we're asked what number of stereoisomers can this thing form? And with this, what we need to know is recognise this is a transition metals topic. And we really want to remember what kind of stereoisomers we can get with this transition metals topic. And we can either have cis-trans, or we can also have optical. But to have optical, we need to have bidentate ligands, or beyond. And in this case here, we want to recognise that we do have a bidentate ligand. We have ethyl diamine as one of the options here. So because this is just multiple choice, I'm going to use shorthand for representing that ethyl diamine. I'm just going to do like a little looping curved line to show it. But with this, I always sort of start my sketches by just doing the sticks. So you could have had the chlorines on the opposites and the ethyl diamines on the opposites as well. That would be one isomer. So that would be the trans isomer. Or we could have the cis isomer, whereby we have, again, just doing my bits around it. Or we could have had the cis isomer, where the chlorines are next to each other, and the ethyl diamines, the bidentate ligands, are next to each other. Now, this is where we've done our cis-trans, but we do also have the option here of an optical isomer, because what we've just done there, the cis version of this complex ion, can also be used to work out the optical isomer. So I'm going to do my little mirror line just so you can see this. So this only really happens with like your bidentate ligands. So now we can do our mirror image, and we have another isomer there. So our answer to this one is 3. We have 3 stereoisomers of this. So the last one here, which of the following arrangement gives the correct increasing order of reactivity of the above compounds with HBr? So I would look at these and I would think, well, what functional groups do I have? I can see that I've got an alkene, and then I've got a carboxylic acid and an alkene, and then I've got another alkene. So not too many differences there really, but we can have a look at maybe like the amount of groups that we have there, and that can sort of help us out here as well. So with this question, the key fact that we want to use is the fact that the more stable a carbocation, the faster the reactivity. And the higher stability of a carbocation generally relates to how many groups surrounding it, okay? So the more sort of methyl groups, ethyl groups, and everything surrounding the carbocation is going to make it faster at reacting. So for that reason here, we're going to start with the ones with the fewer groups. And here we've even got like a C here as well, haven't we? Part C, we've got a carboxylic acid group. So that one here is going to make it the least stable and therefore the slowest reaction. Okay, so straight away we're going to go with C being our slowest reaction. So for that reason we can eliminate B and D. And then the next one, both of them are the same. B is chosen the next, which makes sense again. It's just ethene, which is, you know, it's got no groups, it's only got hydrogens attached to that double bond, so we don't see that like high stability of a carbocation. And then moving on to the next, I think the easiest thing to do is to think, well, what's the other end of the spectrum? What is going to be the most stable carbocation, which is going to be the one with the most groups surrounding it, and that's going to give us our fastest reactivity. And out of these, I can see D is going to be the one which has that highest stability, because I can see 2 methyl groups attached to that. So that would be bang on what I would choose. So my final answer for this one would be A. And that's it. We've managed to make our way through this paper. It has been hard work and it has been long, but you have done brilliantly. Make sure you keep practicing papers. Go over any of these questions you got stuck on, maybe make some flashcards from them with model answers, maybe have a look at some other questions similar, or check out some videos of some explanations just to help you out a bit more. That was really, really good work. Well done for getting through it, and I will speak to you soon. All right then, bye.
Ouch! This is why in some videos I have unexplained scratches.